so excited to measure Al-Biruni's principles.
Our team is trying to see if Al-Biruni's dip angle method works in real practice. We will measure the dip angle by building our own device that maintains a steady horizontal. If we are close to the real radius of the Earth, then Al-Biruni was really onto something. If our value is not close to the real radius of the Earth, then perhaps he was lucky.
Let's consider the history of this project. Who took these early measurements of the Earth? So Aristotle is the first recorded measurement, who took it at 400,000 stades. Archimedes measured it as 3 million stades, Cleomenes at 300,000 stades, and Eratosthenes at 252,000 stades. Now, all of these stade measurements are different, determined by different cultures in different time periods, so it's difficult to add one up to the other and realize what a true distance was. The measurement of Eratosthenes was the most accepted calculation for many years because he improved upon the attempts of his predecessors by using a new instrument called the skiatheron. The skiatheron was a type of astrolabe but modified. And here are Al-Biruni's figures. He did things a bit differently by measuring his mountain in cubits, which is the portion of forearm from the elbows to the tip of the fingers. He approximated the height of his mountain to be about 652 cubits and his dip angle to be about 34 degrees. Where he took his measurements was in the district of Nadanda, Pakistan, and the peak was in the Salt Range. And refraction was not considered in his calculations because it was not even known of at the time. He would have considered the atmosphere to be even all the way from the bottom to its top.
Let's look at the method that Al-Biruni used to get his measurements. Step 1. Climb a mountain near the sea and measure the dip of the horizon when the sun sets. Step 2. Use the above value to determine the mountain's height. Step 3. Use this equation to find the ratio of circumference to the mountain's height. Al-Biruni determined that the radius of the Earth was about 12,851,369.84 cubits. If we calculate that based on Nolino's value, that gives us a radius of about 3,978.92 miles. And the actual distance is 3,963.12 miles.
Procedures. Step 1. Make a device that maintains a steady horizontal used to measure the dip angle. Step 2. Ride the T into Inner Boston and take the elevator to the top of the Prudential Center. Step 3. Lay the measuring device horizontally and pour water to create a horizontal equilibrium. Step 4. Place the eye behind the first soda bottle at the water level. Then look as far as possible, marking the horizon level on the other soda bottle. Step 5. Collect data, calculate the dip angle using trig, and account for refraction. Our device is designed to maintain a steady horizontal using water, which has a natural tendency to quickly reach equilibrium due to gravity. We took 2 plastic soda bottles, cut off the bottoms, and drilled a hole through the caps. Then we attached a rubber nipple to each bottle and sealed them with RTV silicone so no water leaks out. Next, we drilled 2 circular holes in a long wooden board to hold the soda bottles in a vertical position. This helps stabilize both bottles. Finally, we attached both bottles with a flexible rubber tube and filled them up with water. This way, the water helps reach a steady equilibrium horizontal.
We measure 3 different heights to get 3 different dip angles using this formula here, which was derived using simple trigonometry. The dip angles we got were 0.52 degrees, 0.74 degrees, and 0.34 degrees. We averaged them to get an average angle from the horizontal to the horizon, or dip angle, as 0.53 degrees. Now that we have our angle to the horizon from the top of the building, we needed to have the height of the building. Thus we calculated this height using trigonometry and distance d from the base of the building and the angle phi to the top of the building. Using this equation, we used 4 different distances, 4 different angles to get 4 different heights, and these are shown in the table here. We averaged the heights together to get an average of 742.3 feet, a standard deviation of 252 feet, and an uncertainty of 126 feet. We researched the actual height of the building to be 753 feet. Next, we performed Biruni's calculation of the radius of the Earth without accounting for refraction, and this can be shown using the cartoon shown here. We stood at the top of a building of height h and measured the angle theta to the horizon. And plugging in our average value for theta, we get 1.76 times 10 to the 7th feet. Using our maximum and minimum for the limits for error, we got limits for error of 9 times 10 to the 6th feet to 4.3 times 10 to the 7th feet. The actual radius of the Earth is 2.09 times 10 to the 7th feet. And using this and our average radius we calculated, we got a percent error of 15.8%. Shown here is a cartoon of how refraction alters our viewing of the horizon. So an actual particle of light comes in the atmosphere and bends to go to our eye. We see the light coming from an apparent trajectory of down here. Now the difference between the actual introduction and the apparent introduction is delta theta, and that's our correction for refraction. And then we have our actual angle to the horizon as theta minus delta theta. Using this website, we inputted the temperature for the day as 46 degrees and the distance to the horizon to get a correction for the refraction as delta theta equals 0.427 degrees. We then used our equation for the radius of the Earth to get a radius of the Earth as 5.4 times 10 to the 6th feet. Using the same equation and our limits for error of the angle, we get limits for error for the radius of the Earth as 3.63 times 10 to the 6th feet to 8.4 times 10 to the 6th feet. And this gives a percent error of 74%. This is mainly due to our technique. We could not adequately sight the horizon because of the haziness of the day. Our instrument was also off in its measuring. We used a Sharpie that was pretty wide in its marker tip. Also, another way we might have limited the error associated with this would be to use a larger building or a larger structure. A larger height would minimize error further.
Our calculation for the radius of the Earth is much farther off the true radius than Al-Biruni's. If Al-Biruni had corrected for refraction, his radius would have much more error. If we had not corrected for refraction, we would have been within 20% of the true value. The analysis shows that our hypothesis is indeed conclusive. It is possible to measure the radius of the Earth using primitive navigation skills in a high-altitude landmark. However, if refraction is considered, it is likely there will be much more error. The experiment shows that refraction does have a tremendous effect on the dip angle, especially since it's already so small. This results in a lot of deviation from the true radius of the Earth. Thus, with Al-Biruni's ignorance of refraction, he was indeed lucky to have been so close.
The mathematical scale, I don't know if it was that, but I'm gonna let it go.
At night on Wednesday.
He's talking about clouds.
On Wednesday
Well,
night.
the clouds are really pretty. So
Clouds are like there's like a cold front coming. A lot of clouds moving through
About that high
over the
pressure system that
moon.
was sitting over us, that's totally gone.
That's
now.
gone now. Yeah, it's cold. We're gonna get some more precipitation.
Go Primnav.
What's your figure of merit on that one?